When water depths reach over 25 feet, jackup rigs are used to complete the drilling program. Able to drill straight holes, not deviated ones, these jackups usually follow a grid-like pattern similar to those used onshore and in protected waters. Each well has a piled jacket that is either set down over the tree after completion or can be preset and drilled through from the cantilevered floor of the jackup. Wildcat and delineation wells drilled in deeper water with more intense wind and wave action using a jackup, a drill ship, or a semi-submersible will be cemented and abandoned once the appraisal is complete. These holes are considered expendable because the delay in building the platform and the surface facilities to produce and support this field may take several years. Instead, once a platform is deemed necessary, it will be designed for the precise water depth, the intensity of the wind and waves, and the bottom conditions. Constructed onshore and then brought to the site to be reconstructed and installed, the platform will have a drilling rig installed, and the first thing that they will drill is all new holes for production. As the water gets deeper, platform costs escalate sharply, so vertical wells with individual jackets are replaced by multiple directional wells that can be drilled from a single platform. Larger fields, however, can still support multiple platforms. A platform may house all the facilities associated with the rig, or the rig may be tender supported. If the platform is tender supported, this means that next to the platform there is a floating, anchored boat, either ship-shaped or semi-submersible. On this anchored tender are the crew quarters, mud pits and pumps, cement mixing and pumping equipment, pipe and equipment storage, and other necessary equipment. Lines connecting the tender to the platform carry power, cables, water, and mud. After each well is drilled and completed on an offshore platform, the rig is skidded a few feet to the next slot and a new well is drilled. When all the wells have been drilled, the rig is lifted off the platform by cranes on the tender, and then the tender is towed to a new platform. Because crews can be in such close proximity to producing wells and production facilities on platforms, there are two major safety issues that plague those who drill offshore. Unfortunately, there are no easy answers to: 1. Should the production wells be allowed to produce as they are drilled, or should all wells be completed before production begins? 2. Should the treating facilities, a major source of fire and explosion, be placed on the same platform as the living quarters of the crew or on another platform? As you might suspect, the deeper the water, the more economically advantageous it is to have the treating facilities, the producing wells, and the living quarters all on one platform. In the deepest water or in very harsh conditions, a single platform is normally used, either bottom supported or a floater with a tension leg configuration. The cost of having separate platforms for the treating facilities, the production wells, and the living quarters is just too prohibitive. Because of the risks to the people and to the facilities in dealing with highly explosive and flammable oil and gas, offshore platforms should adhere to the strictest fire and safety codes. The high costs and technologies needed to set platforms, either floating or bottom supported in extremely deep water, has increased the use of subsea completions. Subsea completions are where the wellheads are installed on the bottom of the ocean, then connected by pipeline with nearby platforms. Here is an example. In addition, small fields can be developed in the vicinity of older fields that may have surplus facility capacity. Now that the appraisal has been conducted and the wells drilled according to plan, it is now time to start facility site preparation. In site preparation, surface facilities, that allow the crew to perform their jobs to support production are built. These surface facilities include water and gas separators, pipelines, pumping stations, water treatment plants, etc. When at all possible, it is best to house these facilities separately from the crew's living quarters. As explained earlier, though, sometimes this is impossible due to prohibitive costs. Depending on the location of the reservoir, the steps to prepare the site for production can vary along with their financial costs. Site preparation for easily accessible onshore locations near existing highways and pipelines can be fairly straightforward, while site preparation for remote, deep-water offshore facilities is much more complicated. Let me explain. Most onshore site preparations for surface facilities to produce oil are fairly simple in accessible locations near roads and modern-day infrastructure. In Chapter 6, we described the steps involved in preparing a site so that a land rig could be easily moved into place for exploration. For production, the process is similar, thus allowing the production equipment and personnel to easily access the location. The ground is leveled, a drainage system is installed, crushed rock or other surface stabilizing material is spread over the site. In swamps, raised roads, paved with planks, may have to be constructed if they haven't been already. But overall, it is still a relatively inexpensive endeavor. In remote onshore locations, far from modern-day infrastructure, preparing on-site oil production facilities may be more complicated and certainly more expensive. Here, not only access to the site must be built, but also the means to get the hydrocarbons to the refinery must be constructed. This may mean building new roads and/or pipelines. As mentioned earlier, for example, site preparations for developing gas fields must not only be more precise, but can also greatly increase the upfront development costs. Going offshore raises the site preparation costs considerably. In addition, the depth of the water and the intensity of the wind and waves also impact the bottom line. Preparing locations in shallow protected water such as lakes or estuaries, although usually costing more than onshore, are the simplest. Here, we'll explain three types of construction used offshore. In the first, in shallow water, dredged bottom material may be used to raise the location above the water to create an island. In the second, wooden or steel piles may be driven into the bottom to support a wood, steel, or concrete deck. In the third, floating concrete barges are constructed, towed to the site, and then flooded to rest on the bottom. On the island and the deck, surface facilities are built on top after construction is completed. When using the barge, surface facilities are prefabricated on it before the barge is sent to the site. In deeper, unprotected water, surface facilities are constructed on bottom-supported steel platforms to provide the necessary load-bearing space. Built and installed in two sections, these steel platforms consist of a jacket extending from the bottom of the ocean to just above the waterline and the deck section. First, the jacket is loaded onto a barge and towed to location. Second, the barge is then partially flooded and the jacket is launched. Next, the structure is floated horizontally at the surface by flooding selected jacket parts. Third, the jacket is brought slowly to a vertical position by flooding different chambers. This forces the jacket down to set on the ocean floor. After that, steel pipe is driven through the jacket legs deep into the seabed. A derrick barge then lifts the deck sections from a barge and sets it on the jacket. Finally, the derrick barge stacks the prefabricated facility modules on the deck. In isolated, remote sites like the Norwegian North Sea, concrete gravity platforms have been built. Fabricated on land at remote construction sites, these platforms are floated to location and flooded to sink them to the bottom. Held in place largely by their own weight, they may also have a few skirt piles distributed around their piles for further stability. Although needed in deep, unprotected waters to produce the fields there, when the fields are depleted, these steel and concrete platforms must eventually be decommissioned and disposed of, thus further increasing their costs. In very deep water, where steel or concrete platforms are cost prohibitive, buoyant platforms are increasingly being used. A popular configuration of a buoyant platform is the tension leg platform, which is tethered to piled pads on the ocean floor by strings of steel pipe. The platform's movement in severe seas is controlled by keeping the strings under constant tension. In these buoyant platforms, spars or buoyant vertical cylinders are affixed to the bottom and stabilized by anchor lines. These spars minimize vertical motion caused by surface conditions and are thus able to support production facilities in very deep water. In addition, with today's precise, powerful computers that can stabilize movement, seagoing vessels can be temporarily anchored in place and used instead of steel and concrete platforms. Called FPSOs, for floating production storage and offloading vessels, these seagoing vessels can be either ship-shaped or semi-submersible. Used in conjunction with subsurface completions, they are cheaper than platforms because production does not have to be delayed while waiting for one of these mammoth platforms to be built. Likewise, when the field is depleted, these FPSOs can easily be disconnected and moved to another location. As you can see, the economics and technology of preparing a site to produce an oil or gas field depend in part on exactly where that oil or gas field is located. As you may have heard, the easy oil, the oil that is located onshore near existing production infrastructure or in shallow water offshore, has already been produced. In the years to come, oil and gas production will come from deeper, more remote, more hostile, less accessible locations. It will be with newer, better technology that will help determine the economics and feasibility of getting that oil and gas out of the ground and to market. Let's recap. Even with newer and better technology, the location and dimensions of the field that the Wildcat well has tapped into still must be appraised with step-out, well spacing, and infill drilling. When the field is given the go-ahead for production, more wells must be drilled and facility site preparations constructed so that the field can be safely accessed and where the hydrocarbons can be safely separated and transported to market.